Okay, I did send out to you the next mini exam. I sent it via email, right? And I said that I'm not going to provide the test in a handout version, that I'm trying to force you to download that player so you can visualize these things, but I can't force you to have a computer that works. So I do have some students that have computer problems. So because of that, I will hand out a hard copy, but just be warned that without the visual part of this, it might be a lot more challenging than if you had the visual part of it. I do have some options for you if you don't have a computer that you can get this software on. There's some computers on campus that you'll be able to view it from, but I need to figure out where those are. So there it is, and please make note it's due a week from today. So I think it's 5 problems. That extra. Man. All right, let's get going here. So distances. This is kind of where we ended last time, right? Distances. Make sure this is going to work today. I think this is a pretty good little visual here. How do we find the shortest distance between a point and a plane? All right, so you have some plane sitting out here. Where's my plane? Well, here's my plane. I have a point, I have a plane, and I want to know the shortest distance between that point and that plane. So imagine dropping a perpendicular line down onto this plane. What's that distance? Shortest one we can find. So the construction of this, first we need to get some language established. We are given the point, right? The point we're given, we're going to call x1, y1, z1. And the plane we're given is ax plus by plus zz plus d equals 0. And I'll remind you, what is the a, b, and c in the equation for a plane? Those are the components of the normal vector, right? A, b, and c will always be the components of the normal vector. And the normal vector is what on a plane? It's a vector that's perpendicular to the plane. Okay, so if someone gives you the equation of a plane, you always know the normal vector. And if someone gives you the equation of a plane, you always know at least one point on that plane because you can just plug in values of x, y, and z, or x and y, or x and z to try and get the third point to satisfy the equation. So you can always satisfy your equation and get a point on the plane. So we want to know the distance from that given point to that plane. The first thing we're going to do is we're going to choose some arbitrary point. Okay, so here's our point, here's our point. We're going to choose some arbitrary point on the plane, any point we want. Then we construct a vector from that point on the plane to the point we're trying to find, and then we create a vector from the two. So I can talk about this all day, but the visual part of it I think is what's going to make most sense. So let me see if I can get this visually here for us. Okay, here's our plane, right, sitting there in 3D. I want to try to find the distance from the shortest distance from that point to that plane. So I pick any arbitrary point I want, anything I want in that plane. Okay, anything I want. That doesn't look like it's in the plane, does it? Then I construct a vector like that. Do y'all see that? I don't think that point's in the plane. That's just bad coding on my part, but it looks like it is, right? All that matters is it looks like it right now. Okay, so we've got a point on that plane up to the point we're interested in. That's not the distance we're looking for, right? So then what we do is we look at the normal vector of the plane. So there's the normal vector of the plane, isn't it? And since that normal vector can have some length, I don't even know what its length is or don't care what it is, and that vector can slide around, I'm going to just slide it to where it goes right through the point I'm interested in. Just visually, that's what we have here. With me? The normal one is the red one, okay? Now what I'm going to do is I'm going to take our blue vector, which went from the point to the point, and I'm just going to move it so that it lines up with the normal vector. With me still? Okay, now I'm going to get the blue vector that I started with out of there because it's kind of in our way. Now, if we take the blue vector and we project it down onto the red vector, remember vector projections? We project it down perpendicular, then isn't that the distance we're interested in? So it turns out that the shortest distance between a point and a plane is just the projection of some vector onto our normal vector. Do you also follow the idea here? Geometrically, does it make sense? Okay. So what we'll have to do is we'll have to come up with this blue vector and then project it onto our normal. Now go back up to the notes here. The blue vector, I call it B, is the vector connecting the x naught, y naught, z naught to the x1, y1, z1 vector. So the point we picked on the plane to the one up there that we're trying to find, we create that vector, call it B, and then n is our normal vector that we saw before. And so the distance was the component of B onto n. Now I said projection. Do you remember the connection between projection and component? Projection gave you a what? A vector. Component gave you the length of that vector. So the definition of the component of B onto n means really the length of the projection of B onto n is this n dot B magnitude or absolute value over the magnitude of n, which turns out to be all this over here, which I'm not really going to use that formula. I'm going to stick with this one right here. Okay? Any questions? We're going to do a problem. Well, the comp means the length of the projection vector. So when we took that blue one and we shadowed it down, right, that creates a vector that goes from here, stops right there at that top of the black right there. That's a vector, but we don't care about the vector, we care about its length. The length is the component. All right, so our first example here, find the shortest distance between these two parallel planes. All right, so I'm not asking you for the shortest distance between a point in a plane, am I? I'm asking you the shortest distance between two parallel planes. So we have two parallel planes sitting out here, right? I want to know the shortest distance between them. The biggest mistake I ever see in a problem like this is a student will say the distance is 15. All they'll do is they'll look at, okay, look, the only difference is the 5 and the 20, so they must be 15 units apart. But that's not the way it works. If that's the way it worked, it would be too easy, right? Or they divide, look, you divide the whole second equation by 2, and what would you get? X plus Y plus Z equals 10, and then they say, oh, the difference is only 5, so it must be 5 units apart. That's not it either. Because your planes can be like this, or they can be shifted like this. So depending on where it is in space, you know, it doesn't have to lie parallel to the XY plane or XZ plane. They can be oriented however we want. So how am I going to use what I just gave you to answer this question? Okay, we're going to forget that we know how to do, well, the formula I gave you is for a point in a plane, right? So let's throw out this plane and let's just grab one point off of it, right? So forget the plane and grab a point on that plane and then do the formula. So let's start off by, I'm going to start here by finding a point on this plane, on P1. Now to find a point on that plane, I can pick any value x, y, and z that satisfy the equation. So how about 500? Do you agree that 500 lives on that plane? Yes? Now going back to the formula, and I'm not going to go back on this page because you have it, this would be what in terms of our formula? Given a point, I'm reading 10.5.19, given a point x1, y1, z1, and a plane, this is our x1, y1, z1, isn't it? Now, we weren't given it. We had to kind of extract it a little bit, but that's x1, y1, z1. And then given a plane, now we're going to use the other plane as our plane. You could have gone the other way. You could have thrown out the bottom plane, grabbed a point off of it, and then done the top one. But I just chose to do it this way. We can find a short distance between them by first choosing any point on the plane. So now let me find a point on the other plane. Any point I want. So point on P2 is what? 10, 0, 0. Fine with me. Now this is x0, y0, z0 according to the formula, right? That's the point that lives on the plane I'm trying to find the shortest distance to. We will now construct that blue vector from our picture, which was B. And that vector will be the vector that goes from the point x0, y0, z0 to the point x1, y1, z1. So what will that be? -5, 0, 0. Do y'all agree with that? Okay. Now what I need to do is grab the normal, because remember the formula here at the bottom page says I need the absolute value of the component of b onto n, which means n dot b over magnitude n, basically, is what we need. So I need the n vector. What's the n vector? Hold on. I changed some things on this. There we go. Go back to this. N vector is, what is it? 2, 2, 2? You could scale it if you want. The length, the n vector is any vector parallel to the normal vector. I'm just using the normal vector of that plane. Now, remember, I'm getting that from the A, B, C that I grabbed off that equation. Could I have grabbed the normal off the other one? Well, they're parallel, aren't they? The planes were parallel. So I could have used the normal off the other. But don't do that. I mean, I don't want you to get all mixed up with things. Just stick with, the plane we're working with is the one I'm going to use the normal off of. So the distance now should be the absolute value of the component, of b onto n, which is the absolute value of n dotted with b over the magnitude of n, which is, well, the dot product is a number, right? So it's really the absolute value of the number. The only reason we think it's absolute value is because dot products can be negative, and so it's a distance, and we don't want to talk about negative distance. So we absolute value it. Now the bottom one is the length of a vector, and that's got to be positive. So the bottom is 25. Well, let me do the top first. What's n dot b? Negative 10, and then absolute value. I'll put it absolute value -10 over the square root of 2 squared plus 2 squared plus 2 squared. So 4 plus 4 plus 4 is 12. So we get 10 over root 12. And then you could keep going, right? You go 10 over 2 root 3, 5 over root 3, 5 root 3 over 3. I mean, I would have been happy right here. I think I've told you I don't really care too much about anything else. That's the exact distance between those two planes. Yes? Yes. Vector B. Was the vector going from, yeah, it's going from this point to this point. Picture-wise, yeah. Yeah, you could have gone the other way. Yeah, because look, if you would have gone the other way, instead of going from here up to here, you would have gone here down to here, but then that projection onto here is still the same distance. So it would have worked either way. What do y'all think of that? Okay, where's my copy? I think this is my copy. We'll see. I'm sorry, I switched everything and then I forgot where everything was. What's that? The normal? No? What, this n? I'm using the normal vector to the plane. The normal vector to the plane is a vector that is orthogonal to the plane. The shortest distance. If I have a plane here and I have a point, right? Then I could go from here to the plane. That's a distance, right? But if I go from here to the plane, that's shorter. Here to the plane, that's shorter. And then straight down would have been the shortest. But if your planes are oriented sideways, it's kind of difficult to figure out what straight in is. This does it all for us. Doesn't matter what point on the plane I'm using. That first plane, I threw it out because I picked any point. And then we somehow got straight down to the other plane from there. Okay, Control 7. I'm in a little bit of a bind here. I want to save this picture. There it is. Okay. Is this shit on? There we go. All right. Moving right along here. I think we're moving right along. Finding the shortest distance between a point and a line is very different. So you have, your line. We talked about vector equations of lines last time. Now we have a line sitting out in arbitrary space, right? Could be 3D, could be 2D, and we have a point. And I want to know, given any line, any point, what's the shortest distance between that point and that line? That seems kind of tough, doesn't it? I mean, if it was in 2D, then and everything was lined up like this, x-axis, point, it would be pretty easy to figure this out. But as soon as you take that out of 2D, then things can become a little bit weird, a little difficult to do. So we have a way of doing it. And I think what I'll do is I will start off again by showing you the construction of it. But before that, remember that a line is given by the vector equation r of t equals r naught plus tv. And then a point would be some point. So the way we'll do this is I will look at it in 2D. It'll just be easier for us if we look at it in 2D to start. But imagine that all I've done is taken something in 3D and kind of lined myself up with it so it looks like this. Then do you agree that if I pick, let's say, a point on that line, which I could, right? I could always find a point on a line. How can you find a point on a line if you're given the vector equation? If I give you r of t, how can you give me some points on the line? Just let t be different values, right? Let t be 0, let t be 1, and you start getting different points on the line. So I can always find some point on the line by just plugging in some value of t. Then I can spit out another one, right? So now I've got 2. And then what I can do is I can create a vector between the two, right? Now, I could also have just used the direction vector, v. Wouldn't v be a vector that connects 2 points on the line? But just for the construction purpose, I kind of did it by just using 2 points. So that's some vector that's parallel to my line, isn't it? A? A is parallel to the line. Now what I'm doing is I'm going to create a vector that goes from one of the points to the point I'm trying to find the shortest distance to. And then I'm going to have you look at the distance we're interested in. I'm called little d. Y'all see that? Little d. Now there are some relationships on this picture I've put up here. I have that from pre-cal that if this is the angle between these two vectors, right? Angle between two vectors, then sine of that angle is opposite over hypotenuse. Now, hypotenuse is the length of this side, isn't it? The length of B. So that's where I get this formula from. Yes? So if I solve that for D, right, take that equation over there and solve it for D, wouldn't you get, I think it's below it, isn't it? Solve that for D, and we get D is equal to the magnitude of B sine theta. Yeah? Now check this out. This is pretty interesting, all right? What I'm going to do is I'm going to take that formula up there, D is equal to B, magnitude of B sine theta, and I'm going to just, out of nowhere, introduce two things into this. I'm going to introduce these two things. Do you see them? Magnitude of A, magnitude of A. Magnitude of A divided by magnitude of A is 1, isn't it? So I just took that up there, and out of nowhere, I put that in there. Why? Now, here's why. If you remember the definition of the cross product, the magnitude. What is the magnitude of the cross product of two vectors? Isn't it the top? If you go back in your notes, the magnitude of A cross B is the magnitude of A times the magnitude of B times sine of the angle between them. So by introducing that A on top and bottom, I've been able to come up with a way of rewriting everything in terms of a cross product, which is clever. So the distance between the point and the line is the magnitude of the cross product of A and B over the magnitude of A. And that's it. So what is it that you're going to need if you're trying to find the shortest distance between a point and the line? Let me take all this junk out of here so you can think about this again. What is it that you're going to need if you're going to be trying to find the shortest distance between a point and a line? A vector that is on the line, right? So maybe even the direction vector would be fine. And you're going to need a vector that goes from the line to the point. So you have two vectors. Which one is the one in the formula? Which is the one that goes on the line itself? Is that A or B? It's A, and then B is the one that goes from the line to the point. Once you have those two vectors, it's all just computation after that. Find the shortest distance between the point 3, 6, negative 7 and the line through those points. So I'll draw a picture over here. I have 2 points that live on my line, 0, 3, 5. And I have another point, negative 4, 9, 10. And then I have the point I'm trying to get to. That's the point 3, 6, 7, negative 7. And there was a line between these two, right? Now this is in three-dimensional space, but I've kind of thrown it all on a flat page here. I'm trying to find the shortest distance. That distance right there. So I'm going to need to get a vector that goes from here to here. Whoa, sorry. Which I will call, if I'm going to follow the formula, that's A, right? And then I need a vector that goes from here to here, which would be the B. So let's get A. A is negative 4, 6, 5. Vector B is 3, 3, negative 12, right? And therefore the distance, which I didn't label here, little d is going to be the magnitude of A cross B over the magnitude of A. And I hope everyone has now programmed their calculator or figured out a way to cross product now. But go ahead and help. Whoa, that was almost a disaster there. Cross product, if you could, the top, and then get the magnitude of A on the bottom. And let's do decimals here. It's fine if we do decimals. I'm okay with that. What's the magnitude of the cross product on top? 92.6. And the bottom, magnitude of A. So that's square root of all, whatever the heck that. I did this by hand, but. Oh, on the top is 97? Yeah, that's what I got too at home. 97.76 or 77 or something like that. And then the bottom is what, 8.77? Anyone get that for the bottom? By the way, if you want to know what that cross product was, I got negative 87, negative 33, negative 30. Anyone else get that? But then you have to take its magnitude, and then the magnitude of that became this. 8.77 on the bottom. So you get approximately 11.148 or something like that. And again, this is unitless measurement. We don't have, like, if this is miles or inches or anything yet. If someone told us how this space was constructed and how things were measured, we'd be able to put quantities on that. All right. Try and capture this screen again. I think that was it, right? Yeah. Yay, we're done with that section. Okay. Okay. Everyone has the notes for the next section, right? They're not online. Yeah, they aren't online because I can't get them to be printable for you. If you try and print them from that file online, it says it's trying to flatten the image and it takes forever, and it's a real pain in the butt. So, but I have them. Do you need a copy? 10.6? You need 10.6? There should be some in that filing cabinet over there. Trying to find. You were able to get it to print from the web? Okay. I'm going to keep bringing notes. What do y'all have up to? 10.8? Oh, this is the last one you have? Well, we're going to start 10.7 today, sorry. Thought you had to 10.8. I was like, I'm good through chapter 10. I guess not. It's all right. You'll wing it today. 10 what? No, I don't think there's any 10. No. 10.5, 10.6, that's it. So there was nothing there for you? Okay. So that's it then. Yeah, no one has 10.7. All right, this section, we could spend, 4 weeks on this section because it's got a lot of stuff in it. I'm very dependent on the computer to help us visualize, so we're not going to approach this necessarily the way the author approaches it. We're going to study cylinders in quadratic. That's just supposed to say quadratic, not quadratic. Quadraticum. Quadratic surfaces in cylinders. All right, so I'll go through this pretty quickly. Remember, in two-dimensional space, that the general formula for a circle centered at the origin is x squared plus y squared equals r squared. And you vary the radius. Yay. Okay. Next, an ellipse is very similar to a circle as far as the equation. X squared plus y squared, with the exception that each one of those are divided by some constant, a squared and b squared. And then it's set equal to 1 instead of r squared. Notice that if a and b are the same here, we can multiply both sides by, let's say, a squared, and then you get x squared plus y squared equals a squared, which is the equation of a circle. Right? So if a and b are the same, we have a circle. A changes the length of the, what do we call that for an ellipse? We have these major and minor axes. That's the major axis is the one that goes through the long side of the egg-shaped ellipse. The minor is the one that goes up and down. So if you change a, which is a number under x squared, you change its width. If you change b, you change its height. A hyperbola looks like that, and the difference in the equation is only one thing. What is it? A subtraction. Okay? Subtraction between the variables, x squared and y squared. What would happen if I put y squared minus x squared? In other words, I have the y squared term first and the x squared term next. What's that? Yeah, it would just turn it, right? Turn it the other way. So it would be like this instead. Now, if you change a, you do that. If you change b, you do that. Okay? So these are just things to keep in mind. Now, in 2D, we only have the variables x and y. In 3D, we have x, y, and z. So in 3 dimensions, equations involving the variables x, y, and z, I put there not necessarily appearing together. In other words, you can have an equation that doesn't have x, y, and z, all three, and it's still something in 3D. We've looked at this. What is x equals 0 in 3D? That's the yz plane, right? So it's a plane in 3-dimensional space. The equation is x equals 0, but that's still, it's an equation. It doesn't contain y and z technically, but it still gives us something in 3D. So they're all considered to be surfaces. Before computers, 3D imaging and mathematics, was all by hand. Everything had to be done by hand, and they would use this thing called traces to try and figure out what something looked like. They would find the traces of the surface. Traces are created when you intersect the surface with planes which are parallel to either one of those 3 planes. I'm going to do one example of traces, and only one, because it's by hand and it's tedious. So here we go. We're going to start with our first quadratic surface. Our first quadratic surface is called a cylinder. And the traces, which we haven't really talked about, the traces of cylinders are circles and lines. So here's a cylinder, all right? I want us to imagine coming in here, and let me do this one right here. Let's take the XY plane. There's the XY plane. Where that XY plane cuts through my cylinder, oh, and I can't see the equation. I'm going to scroll down just a little bit so you can see the equation. There it is. See the equation on the bottom? This is the equation of that cylinder. X squared plus y squared equals c squared. C is a constant. Notice z is not in the equation, so we call z a free variable. It's free. It can be whatever it wants. So to create a cylinder, your points, x, y, and z, have to satisfy that equation. What does that look like? A circle, right? It's a circle, but you're allowed to let z vary. So a circle that goes up and down, and it creates a cylinder. Now, the whole idea of a trace is if I come in with the xy plane, what's the equation of the xy plane? Z is 0. So in other words, if I let z be 0, what does this look like? So if z is 0, it's a circle with radius c, isn't it? So where that, now I'm going to have to come in here and click this one. You'll see there, forget those vertical blue lines. But do you see where my green plane hits the cylinder? That's a circle. That's called a circular trace. The trace of that plane cutting through the cylinder is a circle. Now what happens if I move my plane, my XY plane? What if I move it? So I change the value z equals 1. So I move that whole plane up 1. Does that have any effect on this? No. So when I move that plane up 1, there we go, I move it up, I still have a circular trace. And then I can move it up and down, and I keep on getting circular traces. You follow that? You have to imagine that the picture of the cylinder is not there, okay? You have to imagine that you didn't have that picture. And so what you did is you started letting z be different values and realized that what you have is a bunch of circles stacked on one another. And they say, oh, that looks kind of like a beer can, you know? All right, so now linear traces. So instead of using the XY plane, I'm going to take the XY plane out of there. Let's instead use the XZ plane. So here comes the XZ plane. Take my traces out. Actually, I have 2 of them, okay? Sorry. I have multiple planes. But do you agree that this is parallel to the XZ plane, both these planes? Notice what happens if I cut that cylinder. What do I get? Where that plane hits the cylinder, what is that geometric shape? Where I hit it. Where this plane comes through, just that one right there, what is that? It's a line, isn't it? It's a line. Now there's a line on the other side too, right? They're lines. So anywhere where my XZ planes hit the cylinder, I get lines. Now what if I change the plane, instead of the XZ plane, the YZ planes that go the other way? I still get lines. So do you kind of understand the idea of traces? What you do is you start with XY planes and you cut up and down and you say, what do those look like? Okay, a bunch of circles. Then you get XZ planes and you cut through and you say, what do those look like? A bunch of lines. Then you cut with the YZ plane, you cut through and you get, oh, a bunch of lines. From those 3 things, you're supposed to be able to figure out what it looks like. If you don't have a computer to draw it, that's your only option. No? I think nowadays you don't need it as much. But it's a skill. See, I'm going to show you how it's done. Okay? There's a technique to it. I mean, you could argue that this is not useful because we would use a computer to do this. Pardon me? Yeah, this is how it used to be done. So here's the thing. I want to try and draw that same cylinder, right? Radius here is what? 3? Okay, I'd like to try and draw that by hand. So I'm going to act like I don't know. It looks like a beer can. First thing I'm going to do is I'm going to do traces using the XY plane. In other words, I'm going to let Z be free, right? The XY plane means Z is 0, right? XY plane. But I want to be able to move that plane up and down. So instead of Z is 0, I want to use Z is 0, Z is 1, Z is 2, Z is -1, Z is -2. So I'm just going to let Z be some constant. I'm going to call it K. Now, let's write down the equation of that we were given. And tell me what happens if you let Z be K. What happens to that equation? Nothing. So no matter what Z is, you've got a circle radius 3, don't you? So what I would do right now is I would tell myself, okay, in 3-dimensional space, if this is X, this is Y, this is Z, then if Z is, let's say, 0, I get a circle parallel to the XY plane, kind of on the ground, right? That's a circle on the ground. If I let Z be 1, it doesn't matter, right? I move up 1, but it's still a circle, radius 3. So now I have another circle up here, radius 3. Then again, let Z go up again. Keep on getting circles. My circles aren't lining up. I'm sorry. Maybe I need a beer. Maybe that's what that means. I'm dreaming of a beer can. It's not allowing me to draw properly. But I get a bunch of circles, right? Up and down. Z has no effect. You got one there? My other class used to joke around and ask me what I was drinking, but okay. That all right? Now that's probably enough to know what it looks like. But the more complicated shapes aren't that easy. So let's act like that wasn't enough. And let's move on now to the next type of traces we're going to do. We're going to do traces using, let's go with the XZ plane. If I'm going to let the XZ plane, if I'm going to use the XZ plane, what variable is held constant? The Y, right? So my Y is equal to some constant K. This is where you're going to see something somewhat interesting happen. Go to your equation now, the original problem, and replace Y, which was a variable, with K, which is a constant. And you get x squared plus K squared equals 9. That's no longer a circle, is it? Because K is a fixed constant, it's a number. So what I can do is I can move the K squared to the other side. And then I can take the square root. And 9 minus K squared is a number. So long as K is what? Between -3 and 3, right? I have some restrictions on K, because if I let K get too big, I'm trying to take square root of a negative number, and that's not going to work. So let's see if we can get our heads around this. If I fix my Y coordinate to be K, that means I've got planes. I'm going parallel to, here's the XZ, right? XZ plane. I just drew it there. If I start moving back and forth with planes like that, where I hit this picture are going to be lines. X equals a constant. And Z can be up and down because Z is free still, right? There's no Z in here. So I get basically an X, a Y, and a Z to be free, which gives me a line. So I got, I don't know, I have to draw them in here. Here's a vertical line. And since it was plus or minus, sorry if I spit on you, I didn't mean to. I don't want to act like it didn't happen. Did I get you? Okay, I didn't get you. All right. Okay, plus or minus, right, gives us 2 lines. So remember when I had that plane cutting through a little while ago, and it cut through 2 places, and I had 2? What would be the exception to that? When would we only have 1 line? At the very edge, right? When K is 3? When K is 3, you get 0, and then on the other end, right, -3. And then I'm not going to do it, but you would do the same thing using the YZ plane, and you would hold your X constant, and you would get the same thing. That's all I'm going to say about traces. Wait. Well, I mean, they're just tedious. That's all. That's all. I mean, if technology, when I was in school, like we didn't have Wolfram Alpha where you just graph a surface. You know, I didn't have it. So, and the best thing we had was these calculators would try to render something in 3D. And you would type in something, and it would be like computing, and then it would be like creating mesh, and then it would try and do a wire 3D thing, and it was just really crude. And now they're pretty good what you can get out of the computer. So, all right, so check this one out. This is, now we're going to start flying through the quadratic surfaces, all right? I'm not going to do the traces. I'm going to tell you what the traces are, but I'm not going to compute them by hand, all right? So here's another cylinder, right? This cylinder opens up a different way. It's not a beer can, right? Beer can's empty. It's laying on its side now. And notice that the beer can comes down which axis? The y-axis, right? And notice that in the formula, it looks just like before, except Your y is missing. Your y is the free one, isn't it? So any equation x squared plus z squared equals a constant squared is going to be a cylinder that opens down your y-axis. The one before this opened up the z-axis, right? And the z was free. So, of course, what's going to happen if I take the x out of there and throw the y in there and let my x be free? It'll come down the x-axis. And that's the only way we're going to orient our cylinders, okay, down the axes like that. Questions? Do you see the traces again? Circular traces, linear traces. Here they are. Next surface, parabolic cylinders. The traces of parabolic cylinders are parabolas and lines. There's a parabolic cylinder. I want you to see the equation of it on the bottom. The equation of it looks a lot like what? Like y equals x squared, parabola. This one is z equals x squared. Your y is free. So it looks like a folded piece of paper that's in a parabolic shape. And it comes down which axis? Down the y-axis. Down again the free variable axis. Now, let's see the traces. If I cut this with the xy plane, what am I going to get? XY plane, imagine the XY plane and coming up through this thing and cutting it. Lines. Here it comes. Here it comes. Okay, do you see it? Now I'm going to throw the traces in there so you can really see them. Do you see the blue lines? Okay, so I get lines in one direction. What happens if I cut it with the YZ plane? YZ plane. YZ. Back and forth. YZ this way. What do I get? Do you see them? This is the blue lines again, isn't it? It's those blue lines. Now, what if I cut it with the XZ plane? There are your parabolas, right? The XZ plane cutting. Well, that's not it. I need to stop looking up there and clicking here. It makes me nauseous. Parabolic, back and forth. Now you see the parabolas? Okay. Now what happens if well, I'm not going to do it by hand. What happens if I take that equation, z equals cx squared, where y was free, it came down the y-axis. If I change it up and I do z equals y squared and let my x be free, it comes down the x-axis. And then, of course, if I do it the other way, it'll go up and down the z-axis. And then remember with parabolas, remember that number c in front? What did the parabola do if, you know, the number in front was positive, it went like that, and if it was negative, flip to the other side? So on all these things, you can grab that coefficient and wrap it around. So that x equals y squared, like that z is free, goes up and down the x-axis, the z-axis, but you can change it and flip it to the other side if you change that c. What we need to be able to do in this class is to be able for me to give you an equation and you know what it is, like know what it looks like. That's going to be, now not be able to draw it by hand, but be able to know what it looks like. So these are just flipping over. Now the next one, ellipsoid. On an ellipsoid, every trace is an ellipse. Everything. So there we go. I can show you the planes cutting through here. I can move that plane up and down. You can see it. All those traces are ellipses. You see them? They're red traces now. Up and down, I get ellipses. If I take that plane out of there and I go with the plane that goes through the YZ plane, my ellipses go the other direction. Y'all see them coming back and forth that way? Okay, either leave or stay awake, one or the other. Okay? I know it's not that exciting. It's just three-dimensional surfaces. So, do y'all see those ellipses? Yes? And then, the last one, the other direction. Okay? Ellipsoid is like an egg, 3D egg. No matter how you cut it, planes, you'll always have an ellipse when you cut it. Oh, we didn't talk about the equation. Shit, sorry. What's the equation of ellipsoid? X squared, y squared, z squared, all over constant squared, all being added, all equals 1. Looks very much like a what? Ellipse. Except for, now we throw that in there, right? That last piece gets thrown in there. Now that creates our ellipsoid instead of an ellipse. Next, we're not going to sketch by hand. An elliptic paraboloid. Well, the name comes from the idea that when you cut it certain ways, you get ellipses, and when you cut it other ways, you get parabolas. But, I don't know, I mean, yeah, is that it? Guess so. Let's cut it one way. Cut it with the XY plane up and down. Notice that those are ellipses. See all my ellipses? I just moved that plane up. Yeah, it's, see it? Yep. So if I move that plane up or down, everywhere I cut it, that intersection's an ellipse. Now if I cut it, you tell me, if I cut it with the YZ plane, what's it going to look like? Parabolas. There they are. See them? Back and forth, parabolas. What if I cut it with the XZ plane? Parabolas again. So it's called an elliptic paraboloid. What's the equation of elliptic paraboloid? This is interesting. X squared, doesn't the left side look like, what does that left right there look like to you? Ellipse, right? But the other side's not 1, it's that other variable z over c, where c is some constant. So the paraboloid, elliptic paraboloid, doesn't it move up the z-axis, kind of like it's almost like a funnel that goes up the z-axis? Well, if that's the way it works, then I should be able to swap variables out here, do x squared, z squared, and put a y over there, and then it should open up another axis. Or I should be able to go y and z and then go down the x-axis. And I think that's what you have in your pictures, right? Don't I do that? Do I have every one of those? Yeah, there we go. That's going to go down the y-axis. I could change any of these. Like I could pop that thing over to the other side. Oh, I didn't make it where I could pop it to the other side. Oops. Oh well. Yeah. This one comes down the x-axis. Next surface, hyperbolic paraboloid. So the traces are hyperbolas and parabolas. These start looking kind of crazy. But a hyperbolic paraboloid is a great Cal 3 example of a surface because that point right there in the middle of the origin is what we're going to refer to later as a saddle point. It's a point of a graph where you don't have a max, you don't have a min, but you have something interesting happening there, right? Right? It's not a max, it's not a min. Well, there's lots of different things that we'd ask for. Oh, you mean like later on? Later on, I'll give you an equation or a function. I'll say find the maximums and minimums of the function and saddle points. So yeah, you would start with some function. This is an equation, but you could replace. We will replace z with f of xy. So our function will be a function of 2 variables instead of 1. And then what we'll do is we'll say find the max and min of this function and the saddle point. So we'll have to identify where those points are happening. Right now we're just trying to get acquainted with what some surfaces look like. Okay, shall I do some traces here? Let's go XY plane. Anyone see what XY planes are going to give us? Let me put it in here. Let me move it up a little bit. Do you see what that is? They're hyperbolas. Look, if I come in like this, you might be able to see them. See the hyperbolas? Now, if I actually bring them in with the red lines, there they are. And we have to look at them kind of from the top to see that they're all hyperbolas. And then if we slice it with the YZ plane, this one might not be as obvious. The YZ plane, anyone see what that would be? Parabolas. I went a little too far there. There we go. Can you all kind of see that? Where it slices through, you would get parabolas. And then the last one, what do you think we're getting the last one? A headache? We're there. We've achieved. What are those that way? Parabolas. So in two directions, they were parabolas, right? But in one direction, they were hyperbolas. Hyperbolic paraboloid. What's the equation on this? That looks a whole hell of a lot of like what we just did, doesn't it? Except it's minus. Except it's minus. And then, of course, we could change things up. We could switch some variables around, and your kind of comes out the y-axis now. I don't know. It's harder with this to say which way it goes out. And then this next one should come out the x-axis, kind of coming out at us like that. All right, a cone. The traces of a cone, what are the traces of a cone? The traces of a cone are ellipses and hyperbolas, or possibly lines. It opens in the direction of the isolated variable. So I'll take a look at the equation first. Here's the equation of a cone. That looks a lot like ellipse, but the other side is squared instead of just z, right? We had z over c earlier, now it's z squared. So when you have something like that, it looks like a cone. Quickly through the traces. There's your xy plane up and down. You get ellipses. Here's your yz plane. Hyperbolas. Hyperbolas. That's about as good as I'm going to get. I mean, I can turn it. No, I can't. It doesn't want me to. Do you see them? Up, down like this. Like for every one on top, there's one that matches on the bottom. Okay, cone. So the cones, of course, can go down different directions, right? This one's going kind of, you would say it's kind of going down the y-axis. And notice that the y is on the right side of the equation. That's the way you can remember it. And then the next one, I'm going to have it come down the x-axis, like that. Now, I did say that some of the traces were lines, right? The only way you're going to get a line is right there down the center. Oh, I just went past, right? It's going to be hard to get it. I think I'm on the center. I know. I can't take the red lines out of there. There's some restrictions on this coding that I did in this one that I just won't be able to get around. But where it hits on the top and bottom, here, it goes straight across the other side and straight up like this, and those are just two lines at a cross. That's all they are. But that only happens when, in this case, y is 0. So just FYI, that's why it says that there are lines sometimes as traces here. Okay, we're almost done. A hyperboloid of one sheet. Traces are ellipses and hyperbolas. Cut it in half, it kind of looks like a nuclear reactor, doesn't it? Like, don't they have those, it's kind of the shape that they use for that. There might be something about, how strong this shape is. I don't know. You look into it. Look at the equation. That equation look familiar? Doesn't that look like the exact equation we just had? But bringing that squared term over and putting equal to 1 instead of equal to 0. I mean, so there's all these little subtleties here. Or you could say that looks like a what? Except not a plus. Look back in here. Which one? Lipstick? Elliptic? No, I'm messing with you. Yeah. So, I mean, all of these formulas are just off by a sign, or one of them is squared, or maybe there's a 1 there or not. And that's going to be the challenge of this for you, is I'm going to give you an equation. It's going to have 3 variables in it, and you're going to have to determine which of these it is. We'll get to an example here at the end. What? I don't know. What is it called? Hyperboloid one sheet. And your traces, you've got ellipses and hyperbolas. And then you can go down the different directions. So how would you explain which direction you would be? Just by looking at this, which direction is it? Like the z-axis, right? And the z has the negative on it. So if I wanted to go down the x-axis or y-axis, I just switch those variables up. Last one, a hyperboloid of 2 sheets. So it's essentially that one that we just had, right? The one we just had, except that the center got pinched off. Do y'all kind of see that or not? Imagine taking the previous one. That's not the way I want to go. And I'm not going to be able to pinch it. Yeah, it kind of does it, but if you take the center of that, right, and start to make it more and more narrow, at some point you can get it to come to a point, and then they separate and become 2 different surfaces, and that's pretty much what you have here. Hyperbola of 2 sheets. Hyperboloid of 2 sheets. No, they're actually, so it's like a hyperbola. Hyperbola is like 2 parabolas almost, right? 2 separate curves that never touch each other. This is 2 separate surfaces that all come from the same equation, but they're separate surfaces. And the equation. So notice on this equation, 2 of the variables are negative and 1 is positive. And which axis does it kind of open up and down? The z-axis, which is the positive variable axis. And then you can do all the different variations of that. All right, we'll start with this one right here. Okay, given this equation, reduce it into standard form of one of the surfaces discussed in this section, classify the surface, include any details about the traces and direction of the surface opening. Are you serious? We got to do that? Really? All right, so let's go for this. I need to make that look like something on this sheet of paper. Now, in your book, just FYI, if you do have a book and you do carry it, page 578 has a summary of all these on one page. I should say most of them, not all of them. I'm not going to use that. I'm just going to use this. So what do we have? Equation, x squared, y squared, z squared. That already eliminates some things, doesn't it? Let's try and get x squared. Let's see. Do you want to get everything to one side? Yes or no? Does anyone have an idea of what this is? Let me try and run through these with you. Is it, I'm going to start at 10 point, where are we? 10.6.5. Is it a cylinder? Is it a cylinder? No, why? Yeah, cylinders don't have all three variables in it, right? One of them is free, so it's not a cylinder, okay? Is it a parabolic cylinder? No, because parabolic cylinder has one variable squared, the other one is not squared, and the other variable is free. So it's not a parabolic cylinder. Is it an ellipsoid? Why is it not an ellipsoid? It's got all three variables squared. Yeah, if we move them all over to one side, they're not all positive, first of all, and we don't have equal to 1, so it can't be an ellipsoid. Is it an elliptic paraboloid? No, because elliptic paraboloid has one of the variables linear, right? What the hell is it then? Is it a hyperbolic paraboloid? No, one of those variables. Is it a cone? Ah, cone has everything squared. Two of them are positive. One of them is on the other side, except that we don't have divided by a squared plus b. Well, maybe we do. Isn't x squared being divided by 1 squared? Isn't y squared really being divided by 1 over root 2 squared? What? What's 1 over square root of 2 squared? 1/2, right? And what's 1/2 on the bottom? 2 on top. Isn't that just an a squared, or what the hell, whatever? It's a constant squared, isn't it? Isn't that just a tricky way of writing that? And the other one is z squared over 1 over root 3 squared. Y'all follow me? So this is a cone. It's a cone, man. Now, which way does this cone open? Like, which axis does it go down? The x-axis, right? Because cones open in the direction of the isolated variable. I have it saying. So the isolated variable here is x. So if I were to draw this, it's basically going to be doing something like that. You know, you don't. Beautiful, right? Beautiful. But I'd put here opens down x-axis. That's pretty much all I'm asking for. Identify the equation, put it in its standard form, and that way you can identify. In this case, you would be identifying what A, B, and C are, right? Out of the formula. Questions on that? Getting cold in here. Is it? Is it cold? This whole building, man, they just can't keep it regulated properly. You would think there would be enough heat coming off of all this that I'd be okay up here, but nope. All right, I'm going to copy that real quick. I'm on 4. Clear. The next one, same thing, right? You can already eliminate some things because you've got one variable is not squared. So how could I, if I wanted to, rewrite this? 4x equals y squared minus 3z squared. Do we have any of our surfaces that had a variable that was linear on one side, the other two variables on the other side were squared, and there was subtraction between them? Which one is it? Hyperbolic paraboloid. Okay. You get the idea here? How would you get the numbers? Do that reciprocal thing again in business? So what could I write here? Look at the formula, hyperbolic paraboloid. You have to be careful here. 1/4 on the bottom. Right, I'll put it in parentheses. Not squared, though, because in the formula it's what? X over some constant, right? Now, what about y squared? Y squared over 1 squared. And then minus z squared over 1 over root 3 squared. What node is hyperbolic paraboloid on? Oh, never mind. 1.615. But we're actually doing the one that has x. Wait a minute. Hold on. 13? There it is, 13. But we're doing... Is it 15? I can't read because these are printed out so damn small. Who did this? Yeah, this is the note 10.6.15 is where that is. So it's hyperbolic paraboloid, and it opens which way? Well, this is kind of a weird one, okay? It's hard to tell which way this one opens, but we'll say down the x-axis. That's real kind of, I don't know about that. It's not very mathematical because it does go in each direction forever, so it's kind of tough to say that. But at least we in this class will understand what we mean by that. The x was the isolated variable. All right, you okay with that? These aren't too bad so far, right? I'm like answering for you. Sorry about that. I know. You can view it though. Oh shit. Do we have any? Yeah. Do we have any of these that have like squareds and linear, all of them appearing? No. So you're going to have to complete the square on this. Well, yeah, you'll just have to see what happens. Yeah, so we did not talk about this, but let's talk about it real quick. All of these equations, all of them that I have here, every one of these surfaces was centered at the origin. Just like back in the day, whenever we wrote, when I wrote x squared plus y squared equals r squared, that really came from the formula x minus h squared plus y minus k squared equals r squared. The bottom one is more general, right? That's a circle centered at HK. The top one is centered 0, 0. Everything I showed you today was centered at 0, 0. But you can imagine that you could move all of them around. So like if I take any of these equations, any of them, let's say I had something like x squared over, well, I'll just leave it easy, something like this. If I had that, okay, I could have done this. And all that would have done, it still would have been the same. These two would have been the same basic shape, except having the -1 and the -4 in there would have just moved it. So when you come to this problem, I'm not going to do it today. When you do this problem, you're going to complete the square, and then you're going to look at what you have, and then you're going to realize it's something that you know off this sheet just moved around. Think you could do that? Maybe? We'll see. All right. I realize you don't have the notes for 10.7, but that's where I'm headed. Did y'all see the homework at the end of this? Is it legible off of there? 558, 21 through 27 odd. All this is like what I just did here at the end. Give you some equations, try and classify the surface. I don't recall what the book says. Let me just make sure that I want you to do what it says, 558. Whoa, that can't be the right page. Ooh. I'm off by like a little bit here. Yeah, that's supposed to be 579. Don't know why that is that way. I'll change it here. And it says reduce the equation into one of the standard forms, classify the surface, and sketch it. You don't need to sketch it. Now, I would encourage you to get on Wolfram Alpha and see if you can figure out, does Wolfram Alpha do 3D plotting, 3D graphing? Can it graph a surface? It does, but it's somewhat limited. It's not the same graphing utility that's used on their main program here. The one that I use, the Mathematica. So it's the same sort of kernel, but they have limitations as to what they can push out to the web. But it's still pretty good. Let me close this up. How are we doing on time? Where does the time go? Yeah, we should, huh? I think we should. Although if you didn't come today and turn in your test, that's probably not a good sign. Right? The tests are worth less if you fail the final. That's true. Have you all run the numbers on what would happen if you fail the final? Has anyone run the numbers on that yet? Fail the final. If you get less than a 50 on the final, I'm pretty sure you have to have like 97 or higher on everything else to pass. Yeah, with the bonus, that might be a little different. I don't like doing attendance. I mean, I'm required to. I used to not be required to, but now I have to. I don't know. Yeah, see, what used to happen is that, when at the end of the semester, if you got an F, you got an F. Or if you dropped, you were gone, whatever. Now, if you drop, or if I give an F to a student, I have to be able to say the last day they attended class. And I'm pretty sure that's a state thing. So I have to take attendance every day so that if someone fails at the end of the semester, I can say the last time they were in class. Is it part of your grade? Oh, I was saying in here it's not. No, that's their choice. That's their prerogative. Yeah. Yeah, I guess to make you come. All right, we have about 20 minutes. Okay, well, 15 minutes. Let me see what we can talk about as far as vector functions. This is chapter 10, section 7. We didn't have 10.7 back there, right? It was just 10.6. So you're just going to have to follow along for now. Don't worry about all the formula. Don't try and copy everything I have down. I'll send this out to you. I'll bring copies next time, okay? Let's just try and understand what's going on here. We've already talked about a specific type of vector function. It was a line, remember? R of t equals R naught plus TV. Now we're going to talk about vector functions and space curves. A function, R of t, defined to be the vector f of t, g of t. So instead of having, inside there like numbers and it being a vector, each one of the components of the function of the vector are functions. Now we can do this in 2D or 3D. So we can have a function where we have f and g inside, or f, g, and h. Here t is a real number, f, g are real valued functions. This is called a vector function or a vector valued function. So what happens is, same thing as usual. I plug in a t, it spits out a vector, right? Plug in a t, spits out a vector. What we studied last class was the line. So if I plug in a t, it spit out a point, well, a vector that pointed to a point. The next one would go to another point, and they all lied on a line, didn't they? All those points would lie on a line. Now that condition's not there. It doesn't have to. All it has to do is follow whatever f, g, and possibly h tell it to do. The domain is real numbers. The range are vectors. So that's just me telling you again. What you plug into a vector valued function is a number. What comes out is a vector. Given a vector function, the f, g, and h are called the component functions. Does that make sense that they'd be called component functions? It's the components, but they're functions, so we'll call them component functions. The graph of a vector valued function is a curve in either two-dimensional space or three-dimensional space. Now, curve could be a straight line. So I'm considering a straight line to be a curve. It's a curve with no curve, straight line. But it's not a surface. That's the key. Surfaces, like we just saw, like the ellipsoid and stuff, that's one thing. Vector valued functions in R2, R3 are curves. So it's the path of something through that space. A fly flying through the room here, right? Something like that, as opposed to the carpet is different. That's surface. So here is an example of a vector valued function. Here it is. R of t equals t squared. That's our first component function, t squared. And then the second component function is 1 minus t cubed. And I'm defining it for all t greater than 0. So now what I have is in the red is what's coming out. The blue is where it's pointing to. So right now, what am I plugging in? The red is pointed straight up. What am I plugging in? You can kind of see it right here. Can you all see that right there? I'm plugging in 0. What happens if you plug 0 in here? You get the vector 0, 1. See, this is it right here, 0, 1. So I'm pointed straight up. At 0, I'm straight up. Then I advance. So as I start advancing my t, the vectors it's drawing starts moving this way, right? You see that? And it's following basically every point that it's pointing to is that curve, like that. It's just going to cycle through. So that vector value function draws the path, that blue curve. Okay? Let's take a look at this one. This is in 3D, isn't it? I want to try and talk about what it does before I put it up here for you. Anybody know what letting your x component be cosine t and your y component be sine t, what that would draw? If x is cosine t and y is sine t, what would that draw? Anyone seen that before? What does it draw? A circle, radius 1. It comes from the idea that a circle, every point on that circle, if the angle is, let's say, t, and it's, let's say, radius r, then cosine t equals the x-coordinate over the radius. The x-coordinate is the one on the bottom there. X over r is cosine, isn't it? Adjacent over hypotenuse. And if the radius is 1, then your x is just cosine t. And then what's your y value? Your y is sine t. Sine of t is y over r. And again, if r is 1, you get y sine t. So the x and the y components should draw a circle. But what's happening to the z component? T over 5. It's just getting bigger, right? So this vector valued function is going to try and draw circles, but its z value keeps getting bigger. That's it right there. As t starts, it starts to draw a circle, but your z keeps getting bigger as t gets bigger. Right? That's a spring. Isn't that a spring? From the top, it's a circle. Well, we love functions and we love limits. So if back in Cal 1, we talked about the limit of a function, didn't we? Now we talk about the limit of a vector function, right? A limit of a vector function. So you're bad? That's a 10-point exam bad, right? Do what? What do you get for being on your phone in this class? What's your reward? Well, I wouldn't be so bad about it, but you already fell asleep today. I mean, just then you can leave. I mean, you can leave. It's fine. You're not going to offend me. What offends me is if you're doing that. You know what I'm saying? Okay. So, especially Facebook. Okay. What about this? A limit of a vector function. Limit of a vector function would be, does it make sense that it would just be the limit of each of the component functions? Like if you want to know what happens as t approaches a certain number in your vector function, then you really just want to know what happens as t approaches some number in each of the components. So each component function does something. So this is all the notation for it. If you want to take the limit of a vector valued function, you take the limit of each of the individual component functions, which sounds nice, but I handed out that test, didn't I? Look at your number. Oh, well, here, this will kind of lead us in. This will probably be the last thing I can do today. I would like to know, given this vector function, what the limit as t approaches 0 of r of t is. So according to what I just said, this limit as t approaches 0, r of t will be equal to the limit as t approaches 0 of cosine t. That's the first component function. Limit t approaches 0 of sine t over t. And the limit as t approaches 0 of e to the t minus 1 over t. That's all that note said. You just take the limit of each one. All right. So let's figure out who knows what here. What's the limit as t approaches 0 of cosine t? 1, because cosine of 0 is 1. So that's just going to 1. And I'll pick on you. What's the second one? 0 over 0? L'Hopital's rule? Which would give you what? 1. It'd be cosine t over 1. No, that's derivative. You're doing cosine. So when you take a limit and you get 0 over 0, it's called an indeterminate form, and there's different ways to do it. But L'Hopital's rule, which, God, I hope you've come through Cal 2, at least seen this. If you haven't seen, well, yes? Okay. L'Hopital's rule is required here, or not required, but makes it a lot easier to do. You take derivative of top and bottom separately, cosine t on top, 1 on the bottom, and you reapply the limit, you just get 1. Next one. If you plug in 0, you get e to the 0 minus 1, so you get 1 minus 1. And on the bottom, you get 0, 0 over 0. L'Hopital again. If you do L'Hopital on that, what do you get? E to the t over 1 So it's just e to the 2 and e to the 0 is 1. So you get 1, 1, 1. So the limit as t goes to 0 of this vector valued function is the vector 1, 1, 1. But let me ask you, this is important. Is this vector valued function defined at 0? Or sorry, yeah, at 0. Is r of 0 defined? No, it is not. You cannot plug 0 into that vector valued function. What you can do, though, is get closer and closer to 0. And as you get closer and closer to 0, it's trying to spit out this vector. It may never spit it out, but it's getting closer and closer to that vector. Remember, 1, 1, 1 goes out 1, up 1, right? So it's pointed like this, out in the first octant, out 1, 1, 1. So that's where it wants to head. This vector value function wants to take some path that heads there. Never can get there, though. That make sense? I'll do a little screenshot of that. Did I miss an S? If I did, I'm sorry. I believe the S is there. No? Shall we? No, shall we resolve it? I'll resolve it right now. I always use the L or the H over the equal sign, so. There's an S. You don't pronounce it, you don't say it, but it's L'Hôpital. Let's see if we have anything else that we can. Let's see where we're headed, I guess. Okay, so I'll just real quick through this. We'll come back. We'll start here next time. But as you might think, we're going to do limits, right? Once we had limits in Cal 1, we talked about continuity, right? Once we have continuity, eventually we get to differentiability. In other words, derivatives of vector valued functions. First derivative, second derivative, third derivative. And then eventually we get to integration too, where you integrate over vector valued functions. And then, before we do integration though, we're going to have the idea of if you're traveling along a curve, then at every point on the curve, there's some tangential vector. Where if you're traveling there and all of a sudden you're cut free and just left to just go in that direction forever, that would be, the red would be which way you would go, and the length of it would be how fast you would be going. So we have this tangential vector instead of a tangent line concept that we'll be talking about. And then we have what's called the unit tangent vector, which will just take that same red vector, but we'll say, hey, I don't really care about its length, I care more about its direction, so we'll just look at that. Second derivative, smoothness, differentiation rules for vector valued functions, orthogonality. Notice on this one, on this circle, which is a vector valued function, notice something about the tangent vector. It is always orthogonal to the vector function. See, the vector function is r of t, goes straight out, doesn't it? The tangential vector is always orthogonal to it. We can show that that's always true. And actually, see, we show it right here. Okay, we'll have to stop. On the one I just handed you, the mini exam, on number 4, the limit, yeah, so that's what I was alluding to earlier. On number 4 on the take-home, that's due next Wednesday, on the y component, that is t raised to the 1 over t. You need to show me on number 4 all those limits done by hand. No, Wolfram Alpha told me that the limit as t went to infinity of this was this. You got to show it all by hand. You should be able to actually do everything on the take-home exam except number 4. Except number 5. 5 is the only one that you shouldn't be able to do with what we have so far. Have a good, what is it, weekend already? Yeah, have a good weekend.